So in general, we know how this fatty acid synthase works, right? By binding a malonyl-CoA on its right side, and then adding, you know, the growing carbon chain to that malonyl-CoA, spitting off carbon dioxide each time. So now we have to think about how this works, right? And what are the reactions that actually turn this into a fatty acid, not just a bunch of acetyl groups. So let's bind, you know, a malonyl-CoA here to an acetyl-CoA, right? Imagine this is on the left side of fatty acid synthase, and this is on the right side. You know, as these two are joined together by the enzyme, we lose our carbon dioxide, and then what we end up with is a 4-carbon chain, right? Our acetyl group here bound to the 2 carbons from our malonyl group, right? And this is bound, you know, really to the enzyme. Okay. Now this looks a lot like a fatty acid, but it's got 2 of these carbonyl groups, and so we have to get rid of one of these things, and we're going to get rid of this one through a set of reactions that are really the opposite of how we, you know, catabolized or broke down fatty acids. So the first step is really to reduce this carbonyl to an alcohol, the opposite again of what we did when we were breaking down fatty acids. CH2, this stays the same, so forth. Okay, now this is a reduction reaction, and so it's going to take some reducing potential, and we're going to use our NADPH, right? We said this P, it stands for a phosphate, really, a phosphorylated NAD, but we see those NADPs when we're synthesizing stuff. So in order to reduce this carbonyl to an alcohol, we have to oxidize our reduced cofactor here to form NADP. So this takes a little bit of reduced cofactors, some potential energy, in order to synthesize these fats. Okay, and this is a, you know, we can think of this as a reduction reaction here. We're reducing the carbon chain. Now, next step, again, is sort of the opposite of what we saw when we were breaking down fatty acids. We need to get rid of that alcohol, and the way we do that is by dehydrating this. So instead of hydrating an alkene to form an alcohol, we're dehydrating an alcohol to form our alkene. So this is a dehydration reaction, loss of water ends up with this alkene. And then the last step, in order to turn this just into a long alkane, a fatty acid, is to, you know, get rid of that alkene to form our fatty chain here. So we have taken this alkene, turned it to an alkane. That is a reduction, and again, we're going to need some reducing potential, and our NADPH is used for this second reduction. Okay. Now, what happens to this growing chain? Really, we saw in the last video that this is in the right-handed binding pocket in our cartoon. It's going to shift to the left-hand side. The right side will bind to another malonyl-CoA, which will get added to the start of this growing chain, and then we will reduce down the extra carbonyl group. Okay, so at the end, I guess we can say there's a transfer of this growing fatty acid onto the different binding pocket of fatty acid synthase so that it can bind to the next malonyl group. Okay, so if you look at these reactions, they really are the opposite of the reactions that we learned when we were building or breaking down fatty acids, right? We would have a fatty acid, we would have to oxidize it to form an alkene, um, and that would generate a reduced cofactor, FADH2. Then we would hydrate it, right, to form an alcohol group with the addition of water. And then this alcohol group would be oxidized to form our carbonyl group with the formation of NADH. Um, and then we would bind to another acetyl group. Okay, so it's very similar, just the reverse of these reactions. The real difference is we're starting with this charged malonyl group. So every time we add 2 carbons, we have to use an ATP to charge it up as a malonyl group with the addition of a carbon dioxide. So that's a little different, right? When we were breaking down fatty acids, we just sort of activated our acetyl group once, and that costs 2 ATPs. When we're building fatty acids, it costs us 1 ATP for every 2 carbons that we add. And, it uses these reduced cofactors also, which there's a cost to that reduction potential.